Good morning. Moving into Unit 8, Lesson 2, we're going to look at how you can make a logarithm into exponential form and then how to evaluate a logarithm. Recall that exponentials are 1 to 1 because they pass the HLT. Which means that exponentials have an inverse, and that inverse happens to be a logarithmic function. So we're going to begin by finding the inverse. Remember, this means inverse of 2 to the x power. So remember that f of x equals 2 to the x power is just y equals 2 to the x power. To find an inverse, you're going to trade your x and your y values. So we have x equals 2 to the y. And then we need to resolve for y. Well, when we're solving this one for y, it becomes log base 2 of x equals y. And so that's what you would graph. Your function is equal to log base 2 of x. So we can switch back and forth between log base a of x equals y to a to the y equals x. And that's what this means. So logs are really exponents. And that's it. They're just rewritten in a different form. Okay. So the inverse of an exponential function is a logarithmic function. Oops, sorry. And vice versa. Okay. So special cases for logs, we have our common log, which is the one on your calculator. It's a base 10, and we just write log. They're not written with a base at all, but you can assume that when you see just log, it means log base 10. Okay, this is your base. And then E, we write it as ln. So if you have log base E, you're going to write that as ln. Okay, so the special cases, both of these have a button on your calculator. In order to get a base on your calculator, most graphing calculators have it now where you can go in and change and just type in the base, but some of the older models do not. I'll have to show you how to go about graphing that. A lot of the times we're going to have to switch it to exponential form. So just know, not like this. Okay, like this. So log of x or ln of x, something like that. All right, so express the equation in exponential form. If you have log base 7 of y is equal to z, the base from your log is the same as the base for your exponential form, and it kind of makes just this swoopy motion. All right, so this would be 7 to the z is equal to y. So a log is equal to an exponent. A log is an exponent, or y is equal to 7 to the z power. Okay. On this next one, we're going to go the other way again. The base here is the same as the base of our log. We don't put log base 10, so we just write log of x is equal to the exponent. A log is equal to an exponent every single time. So log base x is equal to 5. So that's how you would switch these back and forth. Okay, so the base is the same in your log and in your exponent. Okay, go ahead and fill in the following boxes, switching from log form to exponential form or from exponential form to log form. Okay, and this first one kind of breaks the rule because it reminded you of what the base would be. So 10 to the third equals 1,000. All right, 2 is our base, so log base 2 of 16 equals 4. And then here, 3 to the negative second is equal to 1/9. Okay. All right, so looking at this table and converting things from log form to exponential form or vice versa. Okay, so just a couple more practice. This one breaks the rule and puts the 10 there to remind us what that base is, but that is the base of both exponential form and log form. This would be your exponent, and then this is what it will equal. So 10 to the third equals 1,000. I know that to be true, so that statement makes sense. Log base 2, base stays the same, of 16 is equal to the exponent. A log is always equal to the exponent. And same thing here. 3 to the negative 2 being our exponent is equal to 1/9. Okay, so here is a few of them that I'd like you to try converting back and forth from log form to exponential or exponential to log. Okay, run down the list here and check your answers. Notice that the bases match. So if the 5 is the base on the exponent, it is again the base on the log. Okay, if you have a base of 10, we don't actually put that down. If you have a base of e, we use ln instead. Okay, so noticing all of those patterns as you check here. I did put like the y minus 1 in parentheses so that we know that the log is applied to the whole thing. All right, same thing with the 1/2, that cube needs to be applied to the whole thing. Okay, so pay attention to that kind of stuff. 4 minus y, you can put that in parentheses, but it's in the exponent position. So as long as that's clear, then it doesn't have to be in parentheses. Okay, so moving on. Some special properties of logs. If you have log base a of 1, that is always equal to, and we have to think about a to what power will equal 1. All right, if a is any number. Okay, so anything to the 0 power is 1. So log base a of 1 is equal to 0. Remember, log is equal to an exponent. Okay, same thing here. We can use the same logic. A to what power is equal to a. All right, so if our base and what we're taking the log of match, there's only one possible answer for that, and that is taking it to the first power. All right, anything other than that, if you take it to the second, now you have a squared. All right, so whatever number that is squared. And then here, when we have an exponent on what we're taking the log of. So there's a couple rules we'll look at with logs as to where we can move that when we're manipulating it. But we have a to what power is equal to a to the x power. All right, well, for these two statements to be equal, then whatever is in their exponent position must also be equal. And so this is just x. Okay. And then last, we have a to the log base a of x is equal to what? This is the same as taking log base a of something to equal log base a of x. Well, again, for these to be equal, because this portion is the same, then this portion, oops, must also be the same. And so that is also equal to x. Okay, so just some properties of logs to look out for when you're simplifying and getting ready to evaluate your expressions. Okay, so evaluating logarithmic expressions, we're going to utilize those properties among others. And we're going to look at just that common sense of like what power is this going to be raised to? So remember, you can always convert a log to an exponent. So if I have log base 3 of 1 equals, I can set that equal to x and then convert it. So 3 to the x power is equal to 1 if I forget my properties. All right, so for this one, I can just use my properties here. This one would be 0. Okay, these, my bases match, so that applies to this rule here. So my answer is whatever's in my exponent position, that's just equal to 4. All right, so utilizing those properties, log base 12 of 12 would be what? We're using this property right here, where my base matches what I'm taking the log of, it's just 1. All right, if I have 10 log 5, remember that log is a base of 10. If I set this equal to x, then I have 10 to the x is equal to log. Sorry, I did not convert that right. If I set this equal to x and convert it, then I have log base 10, which is just log of x is equal to the log of 5. Well, that means that x equals 5 then. All right, these cancel each other out because the base is the same as the base on the log in the exponent position. All right, the same thing here. Without setting anything up, this base here matches this base here. So my answer is just square root of 17 because it would go through this whole process. Those two cancel out. All right, go ahead and try this next one. Okay. That one, they don't look identical, so it's easy to forget that natural log is the same as log base e. And so the log base e of x is the same as the log base e, or the natural log of 150. So those have to match. Okay. 16 is a little bit different because we have an 81 here. So whenever this happens, if you have a base and a number, look to see if you can rewrite that number in terms of your base. Okay. So this can rewrite as log base 3 of 3 to the 4th power. So in terms of my base, I get that same number there. Well, now these two match, so this cancels, and my answer is just 4. All right, so we're going to do the same thing here with the 10,000 because log by itself is like a base of 10. 10,000 is 10 to the 4th power. All right. And so these cancel, and my answer is once again 4. Right. If that step confuses you there, your other option is to once again rewrite this as a exponential equation. So set it equal to x and then convert it. 3 to what power, or 3 to the x power, is 81. All right, and then you can just solve for x from there. All right, well, 3 to the x power is equal to 3 to the 4th power because that's 81. So x equals 4. Okay, same thing on this one. Okay, and that continues. If I have here log base 64 of 4 and I set that equal to x, then I can rewrite that as 64 to the x power is equal to 4. All right, well, 64 can be rewritten as 4 to the 3rd power. So that's 3x is equal to 4 to the 1st power. So now 3x is equal to 1 because if my bases are the same, my exponents have to be the same. And this is then equal to 1 over 3. All right, and then one more for good measure. Same thing here. If I have log base 5 of 1 over 25, and I set that equal to x, that means that 5 to the x power is 1 over 25. Okay, well, to get this to flip over, I know that x needs to be a negative number. All right, and then to get 5 to 25, I'm going to square it. So you can work out, hopefully, that x will be negative 2. If not, rewrite this in terms of 5. So 5 to the x power is equal to 1 over 5 squared. All right, flip that over, which equals 5 to the negative 2. And now, hopefully, you can see that x is negative 2. And so it can get a bit tedious, but that's what you're doing each time. So if I have for part A here, log base 3 of 243 is equal to x, I'm going to rewrite this as an exponential equation so that I can find the value of x. All right, so 3 to the x power is equal to 243. All right, that's just a matter of figuring out 3 to what power is 343. All right, so what root of 343 is 3 then? Okay, so I know that 3 to the 4th is 81. If I multiply that by 3 again, then I have 3 to the 5th, which would then be, there's 3 and 24, so 243. So x is 5. All right, on part B, go ahead and try this one on your own. Okay, so 3 to the 3rd equals x, so you just have to cube that, and x is 27. All right, so these a lot of times bring back things we've already done. For example, x log base x of 6 equals 1/2 would convert x to the 1/2 power is equal to 6. We've dealt with rational exponents before. To get rid of that, you're going to multiply it by its reciprocal or raise it to the power of its reciprocal. So to do that to both sides, so x equals 36. All right, I have an extra line there. All right, so looking deeper into log functions and what this looks like on a graph. Recall an exponential function, the parent function either looks, let's try that again. Looks something like this, or something like this. All right, for its inverse function. Same thing with the log-based function. All right, only it's inverted. So it's flipped over that y equals x line. So remember, it gets reflected over this line here. So we can see we have one going this way with our 1, 0 intercept. And then we would have the other one going this way. All right, for the natural log of x. The domain of these functions is 0 to infinity. So we have a vertical asymptote at 0. That's because we're dealing with, remember, a log is equal to an exponent. And when you raise something to a power, it will never equal 0. So it's going to approach it but never reach it. The range is negative infinity to positive infinity, or all real numbers. And so our domain and our range, just like with any inverse, are switching places. The function is increasing anytime that your base value is greater than 1, and decreasing anytime that your base value is between 1 and 0. Again, that's no different than an exponential function, because the base of our exponent is the same as the base of our log. The x-intercept of the graph will be 1, 0, flipping around our y-intercept from before. Okay, the graph has a y-axis, has the y-axis as the vertical asymptote. So again, your vertical asymptote is x equals 0. Okay, so knowing all of that, we can then apply transformations to these graphs. So like, for example, number 1, f of x is equal to log base 3 of x plus 3. Based off all of our previous rules, log base 3 of x would be our parent function. From there, this one would move left 3 because it's always the opposite of that h value when I'm looking at and graphing these. And then for the second one, when we graph that, we have log base, f of x equals log base 3 of x minus 2 minus 2. So we are going right 2 from inside here and then down 2 as well from outside here. Okay. All right. Okay, so for this first one, it goes left 3. So remember your original y or x-intercept, excuse me, is right here at the 1, 0. So we're going to go 1, 2, 3. That point moves here. All right. If x is 0, then it's log base 3 of 3, which is just 1. So we know we have a point here as well. And then if x is 6, for example, this would be 9, which is 3 squared. So that's just going to equal 2. And I just used my properties of logarithms to get there. All right, so I have all those points here. So this looks like this. Here with a domain. This time we've shifted left 3, right? So our domain started at 0. So now it goes to negative 3 to infinity. Our range is still negative infinity to positive infinity. By shifting it left, we haven't affected that all real numbers range at all. This is still going to keep increasing. The x-intercept of the function is now at negative 2. And the horizontal asymptote, or excuse me, the vertical asymptote has shifted left 3, so it's now at x equals negative 3 instead of x equals 0. Okay, so we're shifting it following our rules. I did kind of make a table of sorts in my head with the x and the y values. Knowing that we're shifting it left 3, I knew then that our x-intercept would move to negative 2, 0, moving our original one. I knew that if I plugged in 3, that those numbers would match, so I would get 1. And I knew that if I plugged in a 6, I would make this to the first power of 3, making it a 2. So, like I said, I did kind of just do that in my head there. All right, same thing here. We have our original x-intercept would be here at 1, 0. We're going to go right 2 and then down 2. So 1, 2, 1, 2. That point moves there. All right. We can't take the log of a negative number. All right, so when we shift that to the right, we're also moving our vertical asymptote to the right too as well. So where it was x equals 0, your new vertical asymptote is now at x equals 2. And so you have this vertical asymptote line right here. All right. So this actually won't have a y-intercept. I always make my bases match. So for that to happen, I would have to have a 5 in there for my x value. That would be 5 minus 2 is 3. So 1 minus 2 would be negative 1 for my y value. And so at 5, I'm at negative 1. All right, so this is going to curve something like this. And eventually, oops, I didn't go through that point there. Eventually, it would go up and cross my x-axis, I could play with numbers a little bit longer until I've gotten that point. But it would not cross my y. Okay, so domain here is starting at +2 and going to infinity. My range is still going to be -infinity to +infinity, or all real numbers. My vertical asymptote is x equals 2. My x-intercept is at, well, I want this to be 2, which means that this value needs to be 9 so that it is 3 squared. So 11 minus 2 is 9. So 11, 0. Okay, again, that's doing a little bit of fancy finagling in my head. That makes that 9, which is 3 squared, which means that the log and the base cancel, and it's just 2 minus 2 is 0. Okay, so that was a little bit of stuff in my head, but that's what these graphs would look like, shifted. Okay, and that's how you analyze them. And that's pretty much it for logarithmic functions. I apologize for the length of this video. Just let me know if you have any other questions.